The topic for discussion in this video lecture is it's about the foundation for the beginners. So, what is robotics and what is automation? And this is Dr. S. Mohan Lakshmi, Professor and Head, Department of Electronics and Communication Engineering from Rohini College of Engineering and Technology. On completion, the students will be able to explain the types of robots, explain the robo anatomy. They will be able to explain where the robots are really applied. So, what is robo? It's an electromechanical device which can be reprogrammed. It is multifunctional. It is sensible for environment. It can carry out variety of tasks. So you could see in these slide, we have shown different types of robots over here. So which is a manipulator, which is a very essential part of a robo. It's a type of a robo. In the sense, it can pick. So for example, pick and place robots. So where this could manipulate a certain task. And this next one, it's legged robo, where it could walk. And similarly, wheel robo, where it will be having the wheels. And similarly, the last one is the walking robo. And coming to an introduction aspect, so how do we define a robo? It is defined as a computer controlled machine with some degrees of freedom. So what do you mean by degrees of freedom? It is the ability to move about in its environment. So robot typically it will have the sensor to sense its environment. It will have certain goals, then it will have a planning, so to determine how to accomplish those goals, and it will be having the path planning to determine, so in case of moving robots, how to move about its environment using the available degrees of freedom. So this may be the motion of arm to pick something up, or it may be a series of movements where physically it will move it from location 1 to location 2, say. Okay. So the robo usually have a three-phase sequence of operation. So one thing is, first one is it will sense, which is a perception, and the second one is process, which is it will interpret and it will plan accordingly, and third one is action. So it is movement of some kind. So either it can pick and place, or it can move from one place to another, or it can rotate, whatever it is. So why we need robos? So one thing is a speed. So the man cannot do to that much speed, so the robots can do it. And certain places the human beings cannot enter, which may be hazardous or dangerous temperature. So in that place, robots can be deployed. And suppose we want to do any repetitive task, so the normally the human being will get bored of. So we can do the repetitive task with accuracy using the robots. And similarly, any work with accuracy, we can rely on the robot. And this, some of the pictures I have shown you here, this is used in the planets, even in the space. This you call it as planetary robotics. And here you could see a type of humanoids. So where it will resemble the human being, and it is entirely autonomous, where it can do its own function. So here you can see here, the first one is a humanoid, which is actually the name given to that robot is Sophia, where it could even have the emotions. And here you could see certain humanoids which is doing certain works like cleaning, picking up and taking, moving the trolleys, all these things. And how these robots are classified. So we have basically two types of classification. One is based on the Japanese Industrial Robo Association, other one is American. The first one you call it as a JIRA. So where we have class 1 to class 6, where the class 1 is a simple manual handling device. Class 2 is a fixed sequence robo. Class 3 is a variable sequence robo. Class 4 is a playback robo. Class 5 is numerical control robo. And class 6 is an intelligent robo. So you could see from the name itself, you could understand what it is actually. So playback robo is nothing but like once first you will guide that particular robot to do this task, and immediately all those things get stored, and from the next time once it operates, it will take off all the messages or all the commands it has taken, and it will automatically work. And coming to the Robotics Institute of America, which I told in the previous thing, RIA, it has considered only classes 3 to 6. And here they classify it as type A, type B, type C, and type D. So type A is handling devices with manual control to telerobotics. Type B is automatic handling devices with predetermined cycles. So this will know how many times it has to take. For example, I need to pick up certain material 500 times and I need to place it after 1 meter or something like that. So that is predetermined. And similarly, the type C is a programmable server controlled robots which will have point to point trajectories preferably. And type D is very similar to type C, but it will be having the capability to acquire many things in the environment. And what are the basic components of robo? So as I told you, the earlier also I've shown you a thing which is a manipulator or a rover. So this is the main body of the robo, and it will consist of links and joints, and this forms the structural element of robo. And the second important thing is actuators. So this is like muscles of the manipulators, and normally we go for some electrical drives, or that you call it as or the common types used are servo motor, stepper motor, pneumatic cylinders, and end effector. So end effector, this is a part which is a last, which is connected to the last joint of a manipulator, and normally this will handle the objects. It will make connections to other machines, or it will perform the required task. It can vary in size and complexity, where it can fall from an end effector on the space shuttle to a very small gripper. And these are the robo components, as I've told you already, which is sensors. And you have the processor, you have the controller. Of course, we know sensors. This is about it will collect all the information about the internal state of the robo, and it will communicate to the outside world. And robots are often equipped with external sensor devices such as like vision system, cameras, touch and tactile sensors. And similarly, you will be having a controller, which is nothing but you will be having a computer which will control all the motion of the actuators, and it will coordinate this motion with the sensory feedback information. And similarly, a processor, this forms the brain of a robot. So this you want to calculate the motion of a robot joints. So this is probably it will calculate all those things, and that will be utilized. And other important aspect is software. So the three groups of software is used in robo. So one is operating system, which will operate the computer, and the second one is robotic software. It will calculate, as I told you, it will calculate all the necessary motions of each joint, and it will inform the controller. Maybe at different levels. So you can have right from machine language. There are certain languages for the robots, and even it can fall into sophisticated languages used by modern robots. And the third software will be used in collection of routines and application programs. So these robo anatomy and what are the related attributes? So when I talk about the anatomy of robots, it deals with the assembly of outer components of a robot, such as wrist, arm, and body. So you can imagine ourselves. So suppose if I take a hand, we have a wrist, we have an arm, and we have the fingers. So similarly, like this, the very important components over here is joint and links, and based on this the different configurations are made over here. So we have certain robo configurations. So here manipulator of an industrial robo will have a series of joints and links. So roboanatomy deals with study of different joints and links and other aspects of physical construction. A robotic joint provides relative motion between two links of the robo. So each joint will provide certain degrees of freedom. So mostly if you have one joint, there will be 1 degree of freedom. So if you have three joints, there will be a 3 degrees of freedom. So robo complexity can be classified according to the total number of degrees of freedom they possess. So each joint will be connected to two links. So one will be an input link and the other one will be an output link. So from this figure you can see there is a robotic base here, connection which is connected to the first joint, which is termed as link 0. Then the first joint in the sequence, you call it as joint 1. Similarly, you have link 0 is the input link for joint 1, while the output link from joint 1 is link 1, which leads to joint 2. So this joint link numbering scheme is further followed for all joints and links in the robotic system. So you have links and the joints, which is the very important component or of the robot. So here coming to the joints and links, nearly we have all the industrial robot have mechanical joints, which is classified into 5 types as shown in figure below. So this may be a linear joint where it can move linearly, orthogonal joint, you have a rotational joint, you have a twisting joint, and finally you have a revolving joint. So here according to the movement of the robot, these joints are used. So linear joint, you call it as type L joint. So there will be a relative movement. So there will be a relative movement between the input link and the output link. It is a translational sliding motion. Okay. So where the axis of two links being parallel. Similarly, once I go for orthogonal joint, you call it as a type U joint. This will be having a sliding motion, but the input and output links will be perpendicular to each other when they are moving. And similarly, the third one is a type R joint, which is a rotational joint. So this also have a rotational relative motion, where the axis of rotation will be perpendicular to the axis of the input and output links. And once you come to the twisting joint, which I call it as type D joint, so this involves a rotary motion, but the axis of rotation will be parallel to the axis of the two links, unlike the previous one. Revolving joint, which we term here as V, and here the axis of input link is parallel to the axis of rotation of the joint, and the output link axis will be perpendicular to the axis of rotation. And coming to the robot coordinates, so here the configuration, it will follow certain coordinate frames. So before we go into the configurations, we should know how it is denoted. So prismatic joints, it is denoted by P. Revolute joints, it is denoted by R. Spherical joints, it is denoted by S. And suppose if a particular robot is having 3 prismatic and 3 revolute joints, then it is specified as 3P, 3R. So for configurations which is used for positioning the hand of the robot, we have this type of 5 types of configuration, which we call it as Cartesian, cylindrical, spherical, articulated, Scara. So in the brackets, the respective number of joints are given. Say for example, in the first case it is 3P, which is 3 prismatic. In the spherical joint, you can see 2 revolute and 1 prismatic. So from this figure, you can see here the various configurations are given. So this is once again how it is movement. So in the Cartesian, as I told you, it is a 3 prismatic. Prismatic in the sense it is a linear joint. So you can see 3 arrows in the first diagram, which will be moving in 3 linear directions. So once it is given with a rotating arrow, then it means a revolution or rotation. So robo specification. So what does the robo characterize, or how it is characterized? So one first thing is payload. So how much weight it could carry, a robo could carry. Second thing is reach. Reach is nothing but it is the maximum distance a robo can reach within its work envelope. Work envelope is nothing but like how much it could utilize the space. So here also we have 2 types of reach, which is vertical reach and horizontal reach. And here the functions of the robot's joint length and its configurations depend upon this particular reach. And third aspect is precision. It's a validity. How accurately a specified point can be reached. That you call it as a precision. So function of the resolution of the actuators and feedback devices depends on this precision. So most industrial robots have precision of 0.001 inch or even better than that. So even if you have certain error, and if it is going to be a consistent, we can eliminate it. And similarly, the other two characteristics are repeatability, which is a variability. So, for example, how accurately the same position can be reached. Suppose I want to pick a particular material and I want to replace it somewhere else within 1 meter, or say specifically at 1 meter, then suppose 500 times it is performing. So the 500 times it has to do in the same time, and it should not deviate the distance. So that you call it as a repeatability. So how far it is accurate once the task is repeated. Then the final thing is spatial resolution. Spatial resolution is like how the robot could break down its movements into increments. So normally we have a range, and that is specified, or spatial resolution. You can even define it as range divided by 2 power n. So that n will be the movement of steps, or how much it could break down. And once we use the robots, obviously there will be a social and ethical issues. So using the intelligent machines in our daily life, obviously it will bring these problems. So where this is summarized as sensitive task. So normally sensitive task will require human supervision, and humans will no longer take any responsibility for any failure in the robot. And obviously this will reduce the employment and de-skill the workforce. So nowadays artificial intelligence has entered, and it is dominating the robotic world, where it could erode the human freedom. So there are chances of using the AI in unethical ways. So where normally the robots are utilized. So normally in the machine loading, we can place welding, painting, assembly operations, manufacturing, surveillance, medical applications, assisting disabled individuals, hazardous environment, under. On completion, the student will be able to explain what are the types of electric motors used in robotics, and they'll be able to explain the design aspects of stepper motor, and they'll be able to explain the components of servo motor. So here we term here as actuator. It is the term used for the mechanism that drives the robotic arm. There are three main types of actuators: electric motors, hydraulic, pneumatic cylinder. Hydraulic and pneumatic actuators, they are generally suited to drive prismatic joints since they produce linear motion directly. Hydraulic and pneumatic actuators are also known as linear actuators. And what we are going to see is about the electric motors, which is suited to drive revolute joint as they produce rotation. And most of the robots use the revolute joint. So coming to the electrical actuators, so this could be a stepping motor, DC motor, AC motor, or servo motors. Why we go for these type of actuators or these type of motors? So it has its own advantages. Small size, it is easy to control, and you have a high control accuracy. It can respond fast, it is clean. And coming to the disadvantages, it has a low power output compared to the hydraulic actuators. And coming to the electric motors, these are the most common source of torque, which is used for mobility and for manipulation in robotics. The physical principle of all electric motors is that when an electric current is passed through a conductor, normally a coil of wire, which is placed within a magnetic field, a force is exerted on the wire which will make it to move. And what are the components of an electric motor? So these are the principal components. So where you have north and south magnetic poles which will provide a strong magnetic field, and it is made up of bulky ferrous material. So they traditionally form the outer casing of the motor, and collectively it is called as a stator. An armature, which is a cylindrical ferrous core rotating within the stator, and it will carry a large number of windings which is made from one or more conductors. And you have the next component to be a commutator. So this will rotate with the armature, and these are or this consists of copper contacts which is attached to the end of the windings. And obviously the fourth component is a brushes which is in fixed position, and this will be in contact with the rotating commutator contacts. So they carry the direct current to the coils, which will be resulting in the required motion. And as we have discussed, so this diagram shows you the components of an electric motor. So stator, armature, commutator and the brushes. And coming to this electric motors, we have discussed already. So this can be a DC motor, this can be an AC motor, this can be a servo motor. So the DC motor, the stator is a set of fixed permanent magnets which will create a fixed magnetic field, while the rotor carries a current. Through the brushes and commutators, the direction of current is changed continuously, which will make the rotor to rotate continuously. And coming to the AC motor, this is very similar to the DC motor, except that the rotor is a permanent magnet. The stator houses the windings and all commutators and brushes are eliminated over here. And coming to the servo motor, it is a DC, AC brushless or even stepper motor which will have a feedback mechanism which can be controlled to move at a desired speed. And obviously once you are able to control the speed, you can control the torque. So for a desired angle of rotation, I can move it. So you will be requiring a feedback device to which will send the signal to the controller circuit of the servo motor to report its angular position and its velocity. And stepper motor, so from the name itself we could guess, so it will make an incremental rotary motion which is required in a robo, and this is achieved through the stepper motors. A stepper motor possesses the ability to move a specified number of revolutions or fraction of a revolution in order to achieve a fixed and consistent angular movement. This is achieved by increasing the number of poles on both rotor and stator. Additionally, a soft magnetic material with many teeth on the rotor and stator multiplies the number of poles, so which we take here as reluctance motor. And this figure illustrates the design of a stepper motor which is arranged with 4 magnetic poles which is arranged around a central rotor. So you could see that the teeth on the rotor have a slightly tighter spacing to those on the stator, which ensure that the two sets of teeth are close to each other but not aligned throughout. So movement is achieved when the power is applied for short periods to successive magnets. So first magnet, second, third, fourth, like that. Where pairs of teeth are least offset, the electromagnetic pulse causes alignment and a small rotation is achieved. So you can typically achieve 1 to 2 degree. They have several advantages. These stepper motors, it is directly control can be directly compatible with the digital technology. They can be operated open loop by counting steps with an accuracy of plus or minus 1 step. They can be used as holding devices since they exhibit a high holding torque when the rotor is stationary. Coming to the servo motor. Servo motor, they are special electromechanical devices which will produce precise degrees of rotation. A servo motor, it can be a DC or AC or brushless DC motor, and this is combined with a position sensing device. They are also called control motors as they are involved in controlling a mechanical system. They are used in a closed loop servo system. So this gives you the block diagram of servo system where you can see input, which is there is a feedback loop. So once the error is detected, it gets amplified, it is get corrected, and until the error is eliminated, the output is not shown here. Then once you have the proper degree of movement, then the output is shown. Reference input is sent to the servo amplifier which will control the speed of the servo motor. A feedback device is mounted on the machine. This is either an encoder or resolver. This device changes mechanical motion into electrical signals and it is used as a feedback. These feedback is sent to the error detector, which will compare the actual operation with that of the reference input. If there is an error, then the error is fed directly to the amplifier, which will be used to make necessary corrections in the control action. In many servo systems, both the velocity and position are monitored. Servo motors provide accurate speed, torque, and have the ability of direction. On completion, the students will be able to classify the sensors used in robots. They'll be able to explain the operation of various sensors. They'll be able to understand where really the sensors are used in robots. And we'll just see an overview. Okay, like what, why robots need sensors, and how it is classified, and we'll see an overview of various sensors. So seeing this picture, you could see where is the crop line. So you could see a crop line over here. So where the sensor would detect the edges where it is used in autonomous harvesting. Similarly, you could see in a maze, so this is nothing but where I need to spot in an environment. So where am I? So in that case also, the sensor will be used to detect any the path which is open or closed. And robo sensors, it constitute robo's window to the environment. The robo needs sensing to be an active participant in the environment. Each sensor is based on a transduction principle, that is, converting an energy from one form to another. So these sensors will measure a physical quantity. They do not provide the state. So how these sensors are classified basically? So here we have proprioceptive and exteroceptive, which means that which defines it as an internal state or an external state. And so in the first case, it is actually, it will measure the values internal to the system, that is to the robo. Say for example, wheel position, joint angle, battery level. And once it comes to the external state, these observations of robo environment or objects present in it. And similarly, the sensors can be classified as active and passive. So active sensors will emit energy, whereas the passive will receive energy. Say example, the very good example of passive sensor is camera. And this table shows you what is the general sensor classification. So you could see the tactile sensors, wheel motor sensors, and you could see heading sensors. And here we can see that it is divided whether it is representing a state which is internal state or external state. And similarly, you can see that whether it's an active or passive. And this again shows all the thing which is related to the sensors. There is a ground based or motion based or vision based or active ranging sensors. So you can go through this table. And once you are characterizing any sensor performance, so we know that in any real world environment, the measurement is always error prone. So we have various characteristics for the sensor, which are listed as dynamic range, which is nothing but we use it between a lower and the upper limit. The range, again, it is a minimum and a maximum differences. Resolution, it is actually the minimum differences between two values. Linearity, it is the variation in the output signal as a function of input signal. Bandwidth of frequency, it is the speed with which a sensor can provide a stream of readings. And here they are specifically relevant for real world environments, these characteristics. So either sensitivity, cross sensitivity, accuracy, systematic or deterministic error, random error, reproducibility. So we have the various definitions I've listed over here. So what do you mean by sensitivity? What is cross sensitivity? What is accuracy? And other factors. And this are some of the pictures where you could see the different types of sensors, which is tilt sensor, where you have a mercury tilt switch. And here you can see a dual axis inclinometer. So these are the pictures which show you the sensors. And this is a potentiometer. Of course, everyone are familiar with this potentiometer. So this potentiometer, once it is moved or once it is rotated, obviously the resistance also will change. And these are some of the examples of micro switches where it is single direction or omnidirectional, which means that it can rotate in different all the directions, and roller contactor switch. And this is light sensors. Of course, we are familiar with the light sensors, which you would have done in our basic courses, which is a photoresistor, photodiode, differential photodiode, phototransistor, and you could see in this picture the various two types of sensors are represented. And thermal sensor. So it is otherwise it is called as a thermistor. Of course, we know that once the thermal temperature varies, the resistance also varies. And this is proximity sensors. Proximity sensors will be used to detect where the device or the object is located, whether it's a near or far. So normally it is a non-contact, and devices that can be used in these areas that are near to an object can be sensed. So the good examples are photocells, capacitive sensors, inductive sensors. You can see in the picture we have a IR detector and IR LED emitter. Okay, so where the LED will emit and similarly the detector will detect these light, and obviously this is related to the detected object. And here also you can see the photocells where again it will be having a pattern of LEDs and receivers, which is a phototransistors. And we have different type over here. So where you can see in the last one, it is a through beam detectors. Okay, so where the beam will detect, beam get rippled and this gets detected. And capacitance proximity sensors. So once you talk about capacitance, obviously it will generate an electrostatic field. So you can see in the picture it consists of a probe, oscillator, filter, output circuit. So in absence of a target or object, the oscillator will become inactive. So once a target is approaching, the capacitance automatically rises, which will trigger the oscillator. This is the basic principle of capacitance proximity sensors. And very good example of these sensors where it is used. Say for example, when it is properly calibrated, so this could even detect a higher dielectric material through any lower dielectric material. So this is used very particularly, say for example, suppose I want to detect the H2O, that is a water level in the bottles. Position sensors. Position sensors, obviously this can be detected in three ways, or three sensors can be used, which is potentiometer, which we have seen already, resolver, optical encoders. So the optical encoders will detect either a relative position or an absolute position. So here these are wheel or motor encoders. So this will measure the position, speed, direction of revolution of the wheel. So we define this as a odometry. So which is nothing but the wheel movements can be integrated to get an estimate of the robot's position. So this resolution will vary from will have a resolution of 2000 increments per revolution. So this can be either revolute or that is relative or absolute. So we have optical encoders. So the name itself suggests it involves a light. There will be a light sensor. Then there will be a decode circuitry, obviously. And there is a in between you will be having a mask or a diffuser. So this will detect the relative position, where you could see this diffuser will tend to smooth these signals. This is how it is made. So it is like this will tell you the direction or the resolution. So you can see here you have a square wave generated which is denoted by A, and similarly we have one more which is denoted by B. So here the A is lagging the B. And phase lag between A and B is obviously it is from the figure you could see it is only 90 degree. So from this you could detect both the direction as well as the resolution. So these are the possible states. So A and B, we have four different states defined: S1, S2, S3, S4. So we have the combinations of A high and low, that is high low, high high, low high, and low low respectively. And this is where how you detect a absolute position. So you have an LED source and you have a beam expander. So LED will be emitting a light which is expanded, and it is called through the collimating lens and the cylindrical lens. So this is taken to a multi-block encoded disk where it is detected at the other side, such that it will be the light gets focused such that it get you could find a very absolute position. And the next type is a heading sensors. So this can be a proprioceptive, that is, or exteroceptive. This will allow together with appropriate velocity information, which will integrate the movement to a position estimate. So this procedure is called dead reckoning. So where this is used to determine the robot's orientation, that is in which direction it's trying to move, and inclination, how what is the angle of movement. And this is accelerometer. Of course, we know the definition of acceleration, where the force is equal to mass into acceleration is defined. A sensor will be made to sense the acceleration by simply measuring the force on a mass. So the force can be this can be done or sensed through magnetic capacity. And on completion, the student will be able to identify the parameters of transform, preferably used in homogeneous transform, and they'll be able to explain the procedure involved in this convention, and they'll be able to understand what the frame is, and they'll be able to assign the frames. And DH convention. So the idea is to represent each homogeneous transform matrix, which is AI, as a product. So you could see here AI, which is actually given as, which is equal to, we involve two translations. One is rotation, the other one is translation. So rotation is of course we know it is a rotating aspect, whereas the translation is a linear movement. That is rotation and the linear movement. And here the parameters of this transform are known as, so are defined as link length, which is defined or denoted as AI, the link twist, which is denoted as AJ or D, link offset, which is theta, and we have the link angle. So actually AI is a link twist, DR is a link offset, and theta is the link angle. And what are the conditions for existing of these four parameters? So the first one, that is the DH1, the axis X is perpendicular. X1, say for example, it should be perpendicular to the axis Z0. And the axis X1, it should intersect the axis Z0. These two existence of should be considered when you are going to define or conditions, give conditions or comments for the parameters. And how do we assign the frames using this DH convention? So say for example, we are given a robo manipulator, okay, and we have some n revolute and prismatic joints. N revolute and prismatic joints will be there, or prismatic joints, whatever be. The number of links will be always, it is n plus 1. The task is to define the coordinate frames for each link so that the transformation between frames can be written in DH convention. So the algorithm of assigning these n plus 1 frames for n plus 1 links. Suppose I have three links, then I have to assign three frames. So this treats separately first n frames and the last one, which is an end effector frame. And it is recursive in first part so that it is generic. So the step 1. So how to choose the z-axis? So we have to choose the z0 axis along the actuation line of the first link. And second thing is we have to choose the z1 axis along the actuation line of the second link. So for the first link, the axis chosen is z0. For the second link, the axis chosen along the z is z1. And similarly, we need to take how many ever links are there. We need to identify or choose the zn-1 axis. This is the step 1. And once these things are over, that is, we need to finish the job and assign a point on each of the zi axis. That will be the origin of the ith frame. So xi axis for each frame so that two dh conditions hold. So dh1, as we discussed already, the axis x1 is perpendicular to the axis z0. dh2, the axis x1 intersects the axis z0. Y axis for each frame. Step 2. This is the choice of x-axis. Suppose we have chosen the I minus 1th frame and we need to proceed with the ith frame. For the ith frame, the z-axis is already fixed. Of course, we know z-axis is already fixed. And the dh1, dh2, the x-axis should intersect, that is the zi minus 1, and xi should be perpendicular to zi minus 1, and similarly xi should be perpendicular to zi. Is that possible? So there are three cases. So zi and zi minus 1 are not coplanar and they are parallel or they intersect. For all these three cases, it is possible. So where the xi will be perpendicular to the zi. And coming here, zi and zi minus 1 are not coplanar, then there is a common perpendicular for both the lines. And it will define new origin. Say we denote it with O, which is OI, and the x-axis for the ith frame. If zi and zi minus 1 are parallel, then there are many common perpendiculars for both the lines. One of them will define new origin and the x-axis for the ith frame. So it is denoted as OI and XI. If zi and zi minus 1 intersect, then there is a vector orthogonal to the plane formed by zi and zi minus 1. So the point of intersection can be a new origin, and the x-axis for the ith frame is the orthogonal to this plane, so which is denoted by y and xi axis. So step 3. So if you already chosen the vectors, then x and the point y for the ith frame, yi can be assigned by, of course this is not that much important, but this is a cross product operation. And you can see the illustration of DH frame over here in this diagram, which is taken from the one of the robotics textbook. So where you can see we have a joint, three joints, that is joint I minus 1, joint I and joint I plus 1. We have two links, link I and link I minus 1. And you could see here we have the frames here, which is denoted with ith frame, I minus 1 and I minus 2. And assigning the last frame to the end effector. So for most of the robots, Zn minus 1 and Zn will coincide, so that the transformation between these two frames is done by a translation by dn along the Zn minus 1 axis, And the second transformation will be a rotation by theta about zn axis. And this is a planar two link manipulator. We can see we have two links. This is a two link manipulator where you could see all the dh parameters represented in this figure. Say for theta a, that is the displacement, the rotation angle. Similarly here this side also the link to a2, then theta 2, and this is 3 link. So we can see here 3 link cylindrical manipulator, and again you could see here we have the frame which is a base frame which is denoted with x0, y0, z0, and the origin is at o0. And similarly we have a movement here in the second frame. You could see a movement which is denoted with x1, z1, and y1, and the frame movement is denoted by d2. And similarly in the third frame also you can see the thing is given by the linear movement is given by d3. Here we have a particular angle rotation in the between the first base frame and the first frame. And similarly we have the last frame which is denoted with x3, y3, and z3. On completion, the student will be able to explain SLAM. They will be able to explain the applications of SLAM, and even they will be able to represent the models of SLAM. So in a nutshell, what is SLAM? It is a technique used to build up a map with an unknown environment or a known environment, while at the same time keeping track of the current location. So what is SLAM? So computing the robopose and the map of the environment at the same time. That's why it is called as a simultaneous localization and mapping. Localization is nothing but estimating the robot's location. Mapping is building a map. SLAM is making, that is locating the robot as well as building the map simultaneously. So here this is the example of localization for a mobile robot. So this will estimate the robot's poses given the landmarks. So the robot will know the map. Robot knows landmarks of the map on the map, and it will see the landmark and it will want to estimate its pose. So here the yellow stars means that it has a fixed firm information, and these are the round circle which will tell you about the predicted state. Example of mapping. So here robo will create the map. It will estimate the landmarks given the robo poses. So in this case it will not know the map or its part. So though it will know only its landmark, it will know only its pose, and it will estimate the landmarks in the map to create or update, or it will extend the map. An example of a SLAM. So here it will estimate the robo poses as well as the landmarks at the same time. So in the previous case we have seen either it goes for a mapping or it goes for a localization. But once you go for a SLAM, it will take both the things. So the robo does not know the map or its part, and here as usual it will estimate its pose, it will seize the landmark, it will estimate the landmarks on the map to create or update or extend the map. Here also you could see here the dotted line gives a real value, and the other one it gives a predicted value. And this is like a chicken or egg problem. So what we need first, either we need a map for localization or we need a post estimate for mapping. So this is like a chicken egg problem. So why this problem is very important? So this is considered a very fundamental problem, especially for the autonomous navigation, autonomous robots, and this forms the most basis for the most navigation system. So you definitely cannot avoid it. So what are the applications of a SLAM? It is used in a central to a range of indoor, outdoor, in-air, underwater applications, both for manned and autonomous vehicles. So if I'm going to use in home, then it could be a vacuum cleaner or a lawn mower. If it is going to be used in air, it is a surveillance with unmanned air vehicles. Similarly, underwater, underground, space, terrain mapping for localization. So these are the applications where it is given from the as pictures: underground, space, undersea, indoors. So how do we define? So the robo's control will be given, which is specified as U1 is to T, and observation is specified as Z1 is to T. And what we wanted, map of the environment, which is defined as M, and what we really require is the path of the robot. So how it will take from x0 to t at these are the various points x0, x1, x2 till t, various times. So we go for probabilistic approaches. So uncertainty in the robot's motion and observation. Why we go for probabilistic approaches? The reason is the robot motion can be uncertain, and even the observation can be uncertain. So normally we go for probabilistic theory to explicitly represent the uncertainty. So you cannot say the robot is exactly here. So we go for a probability distribution like this, where you could say the robot is somewhere here. So in probabilistic terms, here you could see here the P represents a distribution, X naught is path, M is mapping, and this is given, and we need to have a observations and the controls, which is represented as with Z and U respectively. So this represents a graphical model. So we have the path unknown, we have the controls which is observed, observations observed, and this is the map. So you can see here P x no x0 to t with the map, with the observations and the controls. So we have two types of SLAM, which is called as a full SLAM as well as the online SLAM. Full SLAM is nothing but it will estimate the entire path, and online SLAM will seek or it will estimate only the most recent pose. And you could see in the probability distribution, in the first case it is given as x naught is to capital T, which will take the entire path. Whereas in the second case you could see pxt, which represents only the current pose. So this is the graphical model of full SLAM and online SLAM. Obviously we know that for the full SLAM it is like from the 0th position to the t, the entire path till it takes the entire path. Whereas here you go with for from one pose to the next pose at a particular point of the path. So online SLAM means modularizing out the previous poses. So normally we use integrations, or they are used typically one at a time. So this is represents a graphical model of online SLAM. So where it is represented from x naught t plus x naught to t plus 1. Similarly, when I take for the controls and observation, you need to take the t plus 1 is for z as well as for the u. Why SLAM problem is so hard to solve? So we don't know the path, we don't know the map, so it is both unknown for the robot. And most of the map and the pose estimates are correlated. And the mapping between observations and the map is unknown. And picking wrong data associations can have very divergence catastrophic consequences. And on completion, the student will be able to list out the various type of architectures involved in robotics. They will understand the limitation of the architecture, as well as they'll be able to represent the model of various control architectures. So this is deliberative robo control architectures. So in a deliberative control architecture, the robo first it will plan a solution for the task by reasoning about the outcome of its actions, and then it will execute. So you can see here there is a sensor and actuator. So between this layered structure is there, where it is perception, modeling, planning, then it will execute the task, then finally the control is given to the motor through the actuators. So this is defined or termed to be a deliberative robot control architecture. So the control process goes through a sequence of things, such something like sensing, model updation, and planning these steps. And what are the advantages of this thing, and what will be the problems normally faced? So, advantages, there are reasons about contingencies. Computer solutions can be given to the given task, and these are all goal directed strategies. But the problems are like it tend to be fragile in the presence of uncertainty. We need to have a very frequent replanning, and it reacts relatively slowly to changes, and it may even cause unexpected occurrences. And coming to the second type, which is a behavior based robo control architecture. So, in a behavior based control architecture, the robo actions are determined by a set of parallel reactive behaviors which will map the sensory input and state to action. So, it is very similar to the previous aspect, but you could see here we have various interleaved structures this will find a reason about the behavior of object. It will plan changes to the world, identify, it will monitor the changes, it will build the maps, it will explore, then wanders. So this and all it is done by a sensor. Accordingly, these actions are planned and it is executed through the actuators. And coming to this behavior based control architecture, so here they are relatively very simple behaviors. So each of which achieves a particular subtask to achieve the overall task. So robo can react fast to changes. The system does not depend on complete knowledge of the environment. Emergent behavior. So this results from combining initial behaviors. This could make it difficult to predict exact behavior, and it is difficult to assure that the overall task is achieved. And coming to this complex behavior from simple elements, so it is called as a Breitenberg vehicles. So complex behavior can be achieved using very simple control mechanism. So these are differential drive mobile robots with the two light sensors. So complex external behavior does not necessarily require a complex reasoning mechanism. So you can see here from the figure. So there we define here as coward, love, aggressive. Then it's a behavior. So as it of course we know it is a behavioral aspect. So these are the four types they have defined, and these behavior based architectures are subsumption, so which means one layer will lay on the other one. So this is one of the earliest behavior based architecture. So they are arranged in a strictly priority order where higher priority behaviors subsume lower priority ones as long as they are not inhibited. So from the level 0 to the level n. So again you have one end you have the sensors to sense all these things, and again this is actuated by the actuators. And this is the subsumption example. So this can be performed in the thing. So this is taken from the MIT University. So the source is there. So if you want, you just play this video and just check it. And this is a reactive behavior based control architectures has of course its own advantages and problems. The reactions may not be fast to changes, and thus it does not rely on accurate models. The world is its own best model, no need for replanning. But problems are like it will be difficult to anticipate what effect combinations of behavior will have, and it is difficult to construct strategies to achieve a complex or novel task, and it requires a redesign of control system. Suppose I'm going to give a new task or the robot has to perform a new task. 1 minute. And the third aspect, third architecture is a hybrid control architectures. So this will have the combination of reactive control with abstract task planning. So abstract task planning layer, and we have a reactive behavior layer. So this task planning will tell you about the deliberative decisions. It will plan the goal directed policies. As a reactive behavior layer, it will provide reactive actions. It will handle the sensors and actuators. So you can see here in the behavior set, you have the motors and sensors, and in the abstract task, you have all the behavior activations. And similarly, this also has its own advantages and problems. So advantages, it permits goal-based strategies. It ensures fast reactions to unexpected changes, in unlike in the other two things. And it will reduce the complexity of the planning. But the problem is, the choice of behavior will limit the range of possible tasks. Behavior interactions have to be well modeled, such that it will be able to form the plans. And this is an example of reinforcement learning in a hybrid architecture. So you have different layers over here, which is a policy acquisition layer, abstract plan layer, reactive behavior layer. So in the policy acquisition layer, you will be learning the task without any supervision. And abstract plan layer, you will be learning a system model. There will be a basic state space compression. And reactive behavior layer, there will be initial competence. And so on completion, the student will be able to explain what is telerobotics, micro and nano robots, cognitive robotics. First, we'll come to the telerobotics, which is, of course, it is a remote manipulation. So it is not completely autonomous. So it will be handled by a teleoperator. So coming to the definitions, we should know what is telerobo. This is not autonomous, as I said already, but it is controlled to some degree by human operators. And teleoperator, these are robotic devices that synergistically combine human and machine. And where it is used, so remote manipulation, something like undersea, planetary, hazardous manipulation, where the hazardous materials or the environments are involved. So what are the teleoperation tasks? So the tasks involved are programming, teaching, controlling, commanding and monitoring. So depending upon the location and the nature of the task, issues involved like how far the control level is there. There will be time delays, situation awareness, then similarly the forced feedback. So this shows you the level of control. So where you have machine role and the human task as well as the type of control. So whether it's a supervisory, traded, shared or manual. So time delays. So what is time delay? So it is transmission delay preferably. So how far the information reaches the robot from the remote side, and what is the control action and how it is responded. So the sluggish response need to be controlled, and the time to translate control actions into appropriate machine activities. So that all refers to the time delays. And situation awareness. What is situation awareness? It is like depth perception, image quality, field of view, absolute versus relative judgments of distance, size, etc. Forced feedback. So it is like control force and speed of movement of telerobo. So here force reflection, which is the magnitude of forces or talks acting on an object. So which we call it as kinesthetic, and how these forces are distributed on the manipulator, which we call it as tactile. So what are the advantages here? It is when the forces are applied to the remote area, so it should be kept in mind that there should not be any damage to the telerobo or the objects being manipulated. And similarly, the disadvantages is that obviously we require certain additional processing, so which in turn will increase the delay. And similarly, there will be a increase in the friction and inertia, which will reduce the responsiveness. And of course, we have seen what is teleoperator system, which is a human operator, a human machine interface, and a telerobo. Virtual environment system. So the telerobotics is normally related to the virtual reality. So it is again with the human operator, machine interface, and the computer. So this shows you what is the normal teleoperator system or the virtual environment system. So you have here in the teleoperator system, you have the human machine interface, and here also you have a human machine interface. Whereas here everything is controlled by a computer. In the second case, that is a virtual environment system, where there it is purely by either with the human or the manual. So augmented reality, so it is the where you combine the virtual and the real environments. So the information from the real environment is directly sensed with the display or supplementary information from the virtual environment, and this is overlaid on the display. And this augmented reality, virtual environment, and the teleoperator together we constitute or we call it as a synthetic environments. This is shown over here. So where the human, there will be an interface, there will be a telerobo, you have a normal environment and the virtual environment. And coming to the telepresence, so telepresence, it can be a presence, it can be a telepresence or virtual or synthetic, as we have seen in the earlier slides. So how far the human operator is aware of being present at the site of the interface, or he feels the present in an artificial environment. So this all depends on the transparency of interface and how far you are really acting on it and what type of interaction. So virtual environment and the simulated distinction. So obviously we know that virtual environments, this could be reconfigured. It can create unnatural environments, highly interactive and adaptable, and variety of sensing modalities, strong sense of presence. Simulator is tied to a physical system, virtual environment to the operator. So simulator does far field, where the virtual environment does the near field. And these are certain common characteristics: visual and auditory displays, head mounted display, control signals from head, hands, feet, and speech, haptic interface, which is for manual sensing and manipulation, either with the gloves or exoskeletons. So where these are all normally utilized, these telerobots with a virtual reality or virtual environment, where it is utilized either in the entertainment, defense side, design, manufacturing, marketing, medicine, hazardous operations, education, information visualization, telecommunication, teletravel. These are all the various application domains. And coming to the micro robots, from the name itself we could identify that the robots which are very small. So it is a device having dimensions smaller than a classical watch making parts, that is from micrometer to millimeter. So this will have the ability to move, apply forces, and manipulate objects in a workspace with the dimension in the micrometer or sub-micrometer range. So the micro robots are classified based on task, the size, mobility, functionality. So many robots usually consist of sensors and actuators, a control unit, and an energy source. How it is classified? So depending upon the arrangement of these components which you have seen in the previous slide, so this can be a locomotive or positioning possibility, or manipulation, how far it could do the manipulation, or how could it be controlled, either it's a wireless or wired, or autonomy. The majority of the MEMS based microbiotic devices are developed which is categorized under the movable links. Then micro catheters, micro grippers, smart pills, all this comes under the micro robots. So this micro robotics is quite famous, or it is utilized in the bio micro robotics. So biomanipulation entails such operations as positioning, grasping, and injecting material into various locations in cells. Of course, we know that the cells are very, very small. So you want to inject certain things into this particular cell, this micro robotics are used. So micro robotics and MEMS are interrelated, and they play a very important role in biological studies. Nanorobotics, it is very similar to micro robotics, except that Everything will be in the nano scale. Next is cognitive robotics. So, cognitive robotics. What is cognitive robotics? So, it is endowing the robots with human like cognitive capabilities to enable the achievement of complex goals in complex environments. It is focused on using animal cognition as a starting point for the development of robotic computational algorithms. So, it is a new approach to robo programming based on high level primitives for perception and action. So here it is software agents with higher level cognitive functions that involve reasoning, for example, about the goals or perceptions or action, the mental states, collaborative task execution, etc. Everything is combined. So, so shortly we can say that it is a robotics with a cognitive science. So here, as we have mentioned in the previous thing, it is high level perception and action, attention, memory, learning, concept formation, reasoning and problem solving, social interaction, and the use of language, communication skill. All these things are with the cognitive robotics. And how this could contribute. So here example vision, right? So the typical robotics with the machine approach. So it is bottom up processing of static snapshots. So from raw data to the color segmentation and still further to the edge detection, the object recognition can be done or later to the 3D map. So if you have more snapshots, obviously there will be more work. So perception is mere input to subsequent processing. So we need to do certain subsequent processing. And here it is perception. Normally it will be a constructive one or selective one. So this shows you the traditional cognitive architecture AI, which is of perception, cognition and action. So depending upon the environment, that is sense, plan and act. Thank you.